Joel, today we want to talk about something called the Atwood Machine. Look up. Sorry for those of you at home watching on YouTube. An Atwood Machine is when you have two masses connected by a rope going through a pulley in the middle, so that when one mass goes down, the other mass goes up. And when one mass goes up, the other mass goes, okay? Except now we have to go to our magic physics world. This pulley has no mass and no friction, because that would make the math yucky. Oh, and our ropes don't have any mass either, because that would make the math yucky. So it's really more of a theoretical physics construct, but it's a nice thing for us to wrap our brain around. This is an Atwood machine, except this has a whole bunch of friction in this little pulley here. So the Atwood machine I wrote is a pulley system as seen below. The mass M2 makes it easier for a person or a motor to lift mass M1. Mass M2 is called a counterweight. Oh, got a latecomer coming in. So let's do a little thought experiment, and we're going to vote. So don't blurt out an answer. It says this: suppose I have equal masses, identical masses, are placed on both sides of the pulley, on both sides of an Atwood machine, and they're going to start out at the same height, but then one of the masses is lifted higher, and then we let go. When we let go of this, what happens? A, nothing, the system remains at rest. B, the higher mass falls down because of, gravity. Or C, the higher mass goes higher because of, gravity. Those are our three choices. Did I say choices? Once again, we get to vote. Once again, Christy, how high you hold your hand up is how sure you are of the answer. I'm positive! I'm pretty sure. I'm only guessing because Mr. Dewick will make fun of me if I don't guess, and Mr. Dewick will make fun of you if you don't guess. Nothing wrong with guessing. It's how we make hypotheses. So you understand the question, Michael? Good? Okay. So we're going to raise one of the masses higher, like in this second picture, and we're going to let it go. Who says, A, Mr. Dewick, nothing happens? Boring. 1, 2, 3, 4, 5. Ooh, we're going to have a little controversy here. I like this. This must be a good question. Who says, Dewick, the higher mass is going to fall because, gravity? Who says B, gravity? Ooh. Oh, 1. Sorry, you didn't see that. Who says, no, Dewick, the higher mass is going to go higher when you let it go? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Who didn't vote? Huh? 18. I'm not going to tell you the answer. We're going to prove the answer. This is a job for a free body diagram. I'm going to do a free body diagram on the right-hand side, but I'm going to kind of zoom in a little bit. So, Cole, my friend, what did you vote?
C.
Let's find out. What are the forces acting on this mass right here? Get the obvious one.
Gravity.
Okay. mg. What else?
Tension.
Yep. Which way?
Up.
Good. Is there a normal force? Is it sitting on a surface? Okay. I think that's it. What are the forces acting on the second mass? Get the obvious one.
Mg.
Now, normally I would call one M1 and one M2, but did it say that both masses are identical? Then why waste letters? I can use M and M. What else?
Tension.
Now, you voted which one?
C.
Which I guess means that you think that this is the winner.
Yeah.
Is that okay? So you're arguing anything that ends up pointing down on the right is going to be a winner plus. Anything that ends up pointing down when it gets to the right, up when it gets to the right-hand side is going to be a
Loser.
Why'd you look at Nick when you said that? Did you see him? Loser. Wow! Nick, Bonson Park, 3 o'clock. You can take him. Overrated. Overrated. So anything that ends up pointing up is going to be loser minus. And this is one of the reasons I give you this method. It lets us handle complicated situations we haven't seen before. And we're going to write an equation for the rope, which means we're going to write an equation like that. Start with the winner. Who did you say was winning?
Mg.
Good. Then I run into a tension. What are you going to call that tension?
Tension 1.
Sorry, it's all one rope, so I don't need to Winner or loser? This tension right here. Loser. Good. Minus T. Now, this tension is also pointing up, and you might be tempted to call it a loser, but if you follow it around the pulley, when it gets to this side, which way does it end up pointing? Which makes it a plus. And this mg, again, you might be tempted to call it a winner, Christian, because it's pointing down. But if you follow it all the way around, on this side, which way does it end up pointing? Which makes it a? He did it again. He went, lose. Oh, man. Oh, that was bad. And do we have forces from more than one mass? So it's going to be m plus m times a. Although, what's an easier to write m plus m? M squared? What's 1m plus 1m? Always put numbers in front of things when you, because then it's obvious, okay? So I'm going to write this as 2ma. Cool. Are we relaxed? No, because what else is happening? Now I'm stressed again because the mg's cancel. What does the whole left-hand side work out to? What? What do 3 dots mean? Therefore, I'll even put that and sound very formal in a proof. Therefore, A is 0. So, Cole, do you want to revise your vote? What's the correct answer? A. It says, using principles of physics, there is a beautiful proof. No words, a free body diagram, and an equation. Drop the mic and walk off. A is correct. So those 5 of you that voted that, well done. This is actually really, really handy. Every elevator that you've ever been on, believe it or not, outside of your view, there's a counterweight that's exactly the same mass as the empty elevator. Which means that once the elevator stops and you get off, we don't have to use electricity to keep the elevator sitting at that floor waiting for you. It's going to stay at rest. It's very smart. In fact, all we're carrying, all the motor is having to carry is the mass of the people. The mass of the elevator is canceled out by the counterweight. We've thought of this and we use this in our engineering all the time. So let's solve one. I like example 2, I like example 2, I like example 2. Example 2 is a nice question. In the diagram below, there's a handy generic Atwood machine. Mass 1, David, how big is mass 1? It says. 6.2. Good. You know what? Let's be clever. Let's label it. 6.2 kilograms. Or you could write it right in there, but I think for you folks it's too small to write it right in there, so I'll put it right there. And how big is mass 2? 2.8. Good. I'm going to go equals 2.8 kilograms. Okay. David, what does A want me to do? Wants me to write an equation. I can't. You know what I need to do first? You know what this is a job for? Absolutely. And I usually start on the left-hand side. So let's start on the left-hand side with a 2.8 with mass 2. What are the forces acting on mass 2? Get the obvious one. And since they called it mass 2, I'm going to call it M2G. What else, David, my friend? Is there a rope? Yes. Pointing up. That's what's keeping mass 2 from being in free fall. And those are the only 2 forces on mass 2. What are the forces acting on mass 1? Get the obvious one. Starting to see why I go so systematically. It helps you fill them in systematically. And more than one mass, I'll call it M1G. What else? Tension. And it's all the same rope, Misha, so I can call them both tension. Not, I think, Cole, you had said tension 1. It's all one rope. I know it goes around the pulley. I don't care about that. I'm telling you, tension is going to be the same in that rope. A wants us to write a force equation. Well, I'm going to use winner minus loser. Who's winning? Now you need to think a tiny bit. Which mass is bigger? Which mass is winning? Which force is that? M1. So here's what I'm going to argue, Joel, that you can reason that the bigger mass is going to be the one that's accelerating down. Is that okay? So what we're going to say then here, David, is anything that ends up accelerating, pointing down when it gets to the right is going to be a winner plus. Anything that ends up pointing up on the right-hand side is going to be loser minus. What's my equation? Can you go for it?
M1G
Yes?
minus
Keep going.
T equals
Nope. We're writing an equation for the entire rope.
plus T
Good. What else?
minus M2G.
Now, what does that equal? What does winner minus loser always equal? MA. Do we have forces from more than one mass on the left? We better have forces from more than one mass on the right. I'm just going to start writing M all A. And you can make an argument, Christian, it's always been M all. When it was one mass all of the masses? Well, yeah, it's actually always been that. David, come on with me. Relax, stretch. Come on. Stretch it out. Why are we stretching? Why are we relaxing, my friend?
Loosen tension.
Oh, I love it when I lose tension. Mr. Dewick, you should charge money for these questions. Oh, man. What did A want me to write? A force equation? Emma, we just did. Go ahead. But Emma, just before you go, what does B want me to find? How would I get the A by itself? Divide what? Which M? Yep. And if Emma can do it, oh, sorry. Have a good day, my angel. So change colors, Mr. Dewick. Let's first of all put part B. We're going to get M1G minus M2G. Emma said, Dewick, just divide by M all. And David, if you don't mind, I'm going to put the A equals on that side. Do I know everything there? Do I know M1? Check. Do I know G? 9.8. Do I know M2? Check. Do I know M all? That'll be 6.2 plus 2.8. Let's write out the numbers. A equals 6.2 times 9.8 minus 2.8 times 9.8 divided by 6.2 plus 2.8. What do you get? Oh, David, there's a built-in error check. If I cut the rope, what's the biggest the acceleration can possibly be? So I know the answer is going to be less because the smaller mass is acting like a brake. Right? That's always nice. It keeps you from making a dumb mistake on your calculator. What'd you get?
3.7.
Even? 3 point what?
3.70.
Oh, 3.70 and then 2 repeating? So I'll go 3.70, but I'll store that on my calculator. Meters per second squared. Cool. Christian, what's C want me to find? Tension. Why can't I use this equation to find tension? Because I have a tension deficit disorder. Because the tensions of... I have a deficit of... Oh, it's on. Fine then, Mr. Smarty Pants. How would I find tension?
What are you doing? Oh, Christian, you got hands up.
So how am I going to find tension? I can't hear you, sorry? Okay, so you ready? Here's the strategy. To find A, we look at all the masses because both masses are accelerating at the same acceleration. To find, listen closely, an individual force, we look at an individual mass. Pick one. Now, pause. It doesn't matter which mass you choose, we'll get the same tension for both, but one of them will be slightly easier. The one that will be slightly easier is the one where tension is a winner. Yeah. Ready? So let's do an equation for mass 2. I'll call that part C. So if you look at mass 2, which way is mass 2 accelerating? Who's winning? Which way is mass 2 accelerating? Up. So who's winning? Not M2G, because that's pointing down. This is mass 2, you said? This one, yes? Which way is accelerating? I agree, up. Who's winning? The one that's pointing up. Yeah, don't overcomplicate it. Okay. Who's winning? Who's losing? We're stopping there. We're just writing an equation for that mass now. So what's that going to equal, winner minus loser? Which M? Yes. How would I get the T by itself? How would I move this minus M2G over? Just plus it, no swappy dance. That's why I picked that one. If I had done the other one, I would have had M1G minus tension equals M1A. I would have had the swappy dance. It's one extra line, but honestly, it's not that big a deal. But I'm so lazy, I'll usually pick the one that's easier to get by itself. So all I'm going to do here is plus that over. And I will get tension equals M2A plus M2G. Christian, how big is M2? Oh, 2.8. I still have that written. A. That's why I had to look at both masses first. Okay? I'm going to write 3.7, but what am I going to use on my calculator? Because you have it all stored conveniently. 2.8 plus 9.8. What do you get? Can I do this one in my head? Maybe. 12.8, 13.5, 39, it's right around 40. I don't know. What do you get? Or am I way off? 37.8? Yeah, around 40. Christian, units, tension. It does have units. It's a force. So, newtons, yeah. The only one that doesn't have units is that weird coefficient of friction thing, mu. Really, I'm done the lesson almost. We're going to do a couple more for practice, I think. And then we're going to ask ourselves, what if they don't tell us one of the masses? Can we figure out how big a mystery mass has to be to make this work? Is that okay? So, it says find the acceleration and the tension of these two systems. You know what? I'm going to zoom into this one here. I'm going to kind of draw a little line down the middle of the page. You want to try this one on your own? I'll do it up here. I'll freeze the screen. Let's see if we get the same thing. It wants us to find the acceleration. Then it wants us to find the tension. We're going to do just what David and Christian walked us through. We're going to do a free body diagram, write an equation for everything along the rope. It's going to be winner minus loser equals the mass of all of them times A. Find A. And then Christian will pick an individual mass to find an individual force. So I'll freeze the screen. You try this on your own. See if we get to the same location. Your hint is start with the free body diagram. Actually, you stay here for the remainder of class, okay? Thanks, kiddo. Is that what you got for your first line? Yeah? Under a good stretch. You probably wrote M all times A. I wrote M1 plus M2. I flip-flop apparently like crazy. Christian's getting his calculator out. Good. Now I know he's serious. What hand? Right? Yeah? Okay. Yeah, I'm cold, I know. At least I warned you about the self-esteem thing at the beginning of the year. I think I ended up with that equation for acceleration. And then it's just going to type it in. Again, practice typing these in so that you figure out how your calculator can handle these. I think for these ones, it's going to be brackets around the top and brackets around the bottom. Whew. I got an answer less than 9.8. That's good. Is that right? You got that too? Okay. Now, tension. Tension. How big was M1? 3.5. No. Am I good? I am? In fact, I would argue here, Chloe, the physics isn't too bad. There's just lots of room to make a dumb calculator mistake. So just be cautious. Is that okay? Yeah? Let's try the next one. Ah! Why is this one tougher? Screen's frozen? That's why. Why is that one tougher? What makes this one yuckier? Well, there's a second mass. M. And 3M. No. Isn't it just tougher because I didn't give you numbers? Give you variables? But I heard Cole made actually, for Cole and for anyone, a brilliant observation. Cole, what did you say? It's just... What? Say it again. 3 times larger. So you can do this algebraically, and if you do, you'll find near the end. Was that your phone going off there, Michael? Behind us? Oh, Dalen? Okay, your phones can't make noise. If your phone goes off, next time you owe the class Timbits. It's a rule that's why they're all staring at you right now, because they're conditioned. They're looking for their Timbits. They were all looking at Michael first, and Michael was just sitting here. It wasn't me, Mr. Dewick! So keep the phone dead silent, okay? All right. And by the way, I don't enforce that rule. The mob enforces that rule, and you don't want to mess with the mob. They're going to get their Timbits. So, dead silent. Cole made a brilliant observation. He said, Dewick, all you're really saying is the second mass is 3 times larger than the first mass. If you do this algebraically by letting M1 be 3M and M2 be M, you'll find all of a sudden at the end, your M's will all cancel. They will. And so if you want to try this algebraically, knock yourself out. But if you're not comfy with algebraic, make up a nice number for M. Pick a number. 2. So if this is 2, how big is that? 6. Or you might have said, I'm going to let M be 5. 3m would be 15. You might have said, I'm going to let m be, I would let m be 1 because I'm that lazy. 3m would have been 3. All of us will get the same answer for acceleration and for tension. The only thing, when I'm making up numbers, never let m be 0 because 0 behaves strangely when you multiply or divide. So don't ever do that one. And honestly, you should stay away from 1s too, because what's 1 times 1? 1. What's 1 times 12? Still 1. You might notice a pattern that actually isn't there with other masses. 1 times 1 is 1. 1 times 12 is still 1, isn't it? Oh, sorry. Try that again.
I'm sticking with you, sir.
You know what? Bring that up. For the remainder of the year, Christian, throw that in my face. No. I love it. Because I made a mistake, and I made a dumb mistake. Okay? It's when you multiply the 1 times table, your answer doesn't change, and you might notice a pattern that just isn't there. Okay? I was thinking in physics 12, it's always exponents. What's 1 squared? 1. What's 1 to the 5th? 1. What's 1 to the 9th? 1. What's 1 to the 12th? 1. And so I always tell my kids, even though I said I might have used a 1, don't use a 1, don't use a 0. 2, or often I'll use a 12 because lots of things go evenly into a 12 because I'm that lazy. Anyways, here we go. This is a job for a free body diagram. M1G, tension. M2G, tension. I'm not going to freeze the screen, but I'm going to stop talking. I'm just going to do this. Who's winning? Oh, the 6. I added M1 and M2 together in my head because I was lazy. Do you get that? I'll use the one where tension is a winner. Is there a little buzz coming from my speakers? You know why? My phone, because I switched to Bell over the Christmas break, and clearly Bell gives me much better reception than TELUS, because TELUS I always got 0 bars. My phone is sending out an oscillating electromagnetic field, and when an oscillating electromagnetic field interacts with a speaker, it generates a small current and you get a buzz. You ever been working in the gym, shooting baskets, or playing in the gym, if someone's got their phone plugged into the sound system, and all of a sudden through the speakers you hear that, it's the same phenomena. So what I need to do is move my phone. That's probably going to be far enough. Because it was barely able to generate the current. But now you know why. You get that, 29.4? Did I teach you anything new today? Hopefully not. I showed you a new picture, Atwood Machine, fine. But I'd like to think it was still winner minus loser. Free body diagram. Start out finding the acceleration of everything. Then To find an individual force, look at an individual mass. That's how I always remember it. Is that okay? We're going to pause. I'm going to finish off this lesson next class. So you can put a pause here. I'm going to assign almost all of the homework, but for now, if you want a head start, first of all, a lot of you still owe me the homework. I threw a lot of stuff at you in lesson 7. So you can work on that. You can certainly try number 1, number 2, and number 3 to start out. Quick like a money. You folks said that I showed you the non-Newtonian fluid, that liquid that when you apply a changing force to it, the molecules realign and they behave like a solid? Okay.